Okay, so yes, Sixsenso has been a company that has developed out of the Institute of Photonic Sciences based in Barcelona. And we have developed a technology around the use of fluorescence to identify labeled organisms. So the basis of the technology is to be used in the platform of water monitoring, and we apply the technology to various levels of water contamination, whether it be industrial waters which are contaminated with pathogenic organisms such as Legionella, or we look at the application in marine environments where we would be looking to monitor and allow some degree of control in that monitoring program to control invasive species, which could be transferred from one geographical area into another, such as in a ballast water on a ship moving from Singapore into Europe, transferring those organisms that are damaging to the environment in which they are discharged. We would also look at detection of microorganisms in much more sensitive water applications such as drinking water, residual pathogenic organisms in the water which is produced from a water treatment plant into a potable water distribution system, and also into environmental water management, where we would be looking at monitoring the discharge from water treatment plants into the rivers and the distribution of that processed water back into the environment. The conventional way to monitor is to take a sample and transport it to a laboratory, generate that information on microbiological control, on contamination in a laboratory, and this can take a number of days. Typically, we would be looking at 24 hours to 7 days, depending on the type of organism that you're looking for. And this can influence the ability of the management companies that are operating the facilities to make timely decisions on how the water could be better processed if they had better information on how quickly that contamination could be made aware to the processing facility. So we are looking to develop around a simple system of sample from the source water, which is then concentrated into a smaller volume. And for this, we would use a cartridge filter using a membrane particularly designed for capturing microorganisms. And we would filter a volume of water, 1 liter, 5 liters, 10 liters, and concentrate it in the filter, allowing the elution of that filter to be transferred into a microfluidic station. The microfluidics would be, or is designed around identifying the bacteria that is the target bacteria, and that could be E. coli, Enterococci, Legionella, or any other pathogenic organism, and we would label it using an RNA probe. The technology around labeling with RNA probes is similar to that is used in DNA labeling, but in the case of RNA probe analysis, we would identify the living organism and not just detect the presence of DNA, which would indicate the presence of a historic contamination, but not necessarily identify in one quick test how much of living organism is present. So once we labeled the organism with an RNA probe, we would transfer it into our reader. And the reader is a flow cytometry-based system where the labeled organism, which has got a fluorescent label on it, is interrogated by the reader, and we then develop a signal from that fluorescence which can relate directly to the presence of the organism. And then the system algorithm will then give a level of contamination that's present in the sample taken, and from that we can then work out what the contamination of the original sample was. So we would see that the technology is applicable into a number of applications in water quality management, whether it be an integrated system which is fixed in place within a water treatment facility, or one that is able to be taken to the point of contamination. So the difference between these two applications would be industrial water process monitoring, where they're looking for biofilm buildup in industrial plants, and the control of microbiological reagents to control that bacteria or organic buildup is able to be better managed through a better understanding of what is actually growing inside the water that's filming inside the pipes. Alternatively, we move to on-site monitoring, where we may apply the technology into such things as monitoring beach waters for such contamination as discharges from rivers at high water flow or high rainfall, where the beaches are contaminated with, or potentially contaminated with E. coli or other control pathogens which render it of poor bathing water quality, or into other applications where there is a need to have rapid information on contamination in waters which are located distant from laboratory facilities. We follow a process which allows us to take advantage of the speed at which we can take a sample and report the contamination, which, as we have mentioned, can give managers of the process much more timely information to allow them to make better decision making. So we have a number of comparisons that we would make with existing technologies, which are all of a certain level of capability, but what they lack is the ability to be able to be modular and be applicable in field testing with high accuracy. When we look at a drinking water application, for example, in a sand filter, we would be able to monitor the incoming water for water quality, as well as the exit water at very low levels of contamination. And that level of contamination, that limit of detection, can be enhanced by taking a much larger sample of the original water. So we can get down to very low levels of contamination, 1 CFU per 100 ml. And that is the technology in a summarized format.
Okay, Adrian, thank you very much. Let's continue with the questions and answers block. First question comes from Kirk. He asks if does your device require an autosampler, or is it a probe inserted into a water stream? Can it operate like
there is no probe inserted into the stream. We do not use that technology. the way the technology works is that we take a sample into a cartridge filter. That sample is monitored for volume, and the cartridge filter may filter 100 mils, 1,000 mils, 10 liters, and depending on the sample size that has been identified from some previous evaluation of what is needed to be found in the water itself. So if you're looking for E. coli, for example, and you want to detect at 10 CFU per 100 mil as the reporting level, you may decide that you need to take a sample of 1 liter. The system will take automatically 1 liter into the concentrator, concentrate that sample, and then transfer from that filter into the microfluidics approximately 1 mil of eluent. That 1 mil is used to which has the concentrated bacteria, and it is then labeled with the fluorescent RNA probe. That then transfers into the reader, identifies the presence of the organism, and you report a detection and a count.
Okay. Can it operate by battery power?
The modular system can operate by battery power. We have a design which is to be used for field sampling. So in the case of field sampling, each of the modules would have its own capacity to operate under a battery power, and in that way we can apply the technology into field sampling where there is no obvious electrical capability. In addition, we can operate on a different voltage, say with from a vehicle power outlet. So we have the joint capability of mains and portable power and battery power.
Perfect. What machine protocol does it use to communicate with data loggers?
Well, we would design the software that runs the system will be or is designed to be able to be integrated into another system's software program. So the design would be using a system which can be applied to connect directly with an existing PC-based operating program. It also develops the information that it develops itself is direct readout through a menu system of the control menu, and if there is a specific requirement to design the system around an operator's control system, we would build into it that requirement.
Okay. Another question from Kankel. Could you monitor virus load in sewage waters? It says that it seems that the coronavirus lives for 3 days in sewage waters, and viral charge on it are proportional to number of infected people. Could you monitor anyway?
Monitoring bacteria in sewage is a little bit more complex because there is a significantly higher biomass within the sewage itself. We have many different organisms which may interfere with the ability of the probe to be the signal not drowned out by background information coming from autofluorescing bacteria. So we don't anticipate that this technology will be easily applied into monitoring of raw sewage. However, the monitoring of virus is within the system's capability, but it has been designed around bacteria. And the difference in the membrane structure between a virus and a bacteria is sufficiently different that we would not be able to automatically say that we could detect virus using the system. However, we are interested in looking at the detection of virus using RNA probe methods, but it will have to be a technology which is researched and developed over the next year. The technology that we've developed has been based around bacteria, and virus will be something of interest, but we cannot say at the moment that we have any information that it will be easily resolved.
Okay, thank you. Okay, thank you. Let's go with the last question from Kirk. What is the accuracy of the device compared to the lab analysis?
Oh, it's highly comparative. We have good linearity of bacteria detection from 10 to the 1 to 10 to the 4. The accuracy of detection compares very well with laboratory methods. If we look at the comparison between a culture-based method and an RNA-based method, we can get very comparable accuracies. And the work that we have completed on the detection so far using specific probes has been very comparable to traditional lab-based methods.
Okay, thank you very much, Adrian.